Hi, everyone. Thank you for joining today's IEEE Instrumentation and Measurement Society Virtual Distinguished Lecture webinar. This webinar will be presented by Dr. Liu, and the title is Optical Imaging, Computer Vision, and Augmented Reality for Medical Applications. Before the talk begins, I want to give you a brief introduction to the IMS Society. The IMS Society was kind of founded around this quote from Lord Kelvin in 1883 that says, "To measure is to know." The field of interest of the IEEE Instrumentation Society is the science, technology, and application of instrumentation and measurement. As our mission statement says, the Instrumentation and Measurement Society Administrative Committee strives to provide the most comprehensive and high quality service to our members and related professionals. If you're not currently a member of our society, we really encourage you to visit our website, which is linked down here below, and learn more about our society and the benefits we have for our members. Now to introduce Dr. Yang Liu. Dr. Liu is an associate professor at the University of Iowa. He works with the Department of Electrical and Computer Engineering. His research area focuses on bioinstrumentation, optical imaging, augmented reality, and computer vision. He has served as the principal investigator of grants from the US Army, the US Air Force, NASA, and several other impressive organizations. The imaging instruments that his team developed are currently being used at the Cleveland Clinic in clinical studies. So please join me in welcoming Dr. Liu.
Madison, thank you so much for the very nice introduction. And it's my pleasure to be here. Can everyone see my screen?
Yes, it looks great.
All right. Okay. Yeah, so today I'm going to talk about optical imaging, computer vision, and augmented reality for medical applications. So here's the outline of today's presentation. So first, I'm going to give you an introduction of the technical and clinical background. After that, we're going to look at two aspects. One is the augmented reality and optical imaging for surgery. The second one is multimodal imaging and surgical navigation. And for those two aspects, I will draw examples from my own research to give you some examples. And after that, we're going to talk about some of the future research directions that I think is interesting. So for today's talk, we're going to focus on how do we apply those technologies to solve surgical problems. For those of you who are not familiar with surgery, I assume a lot of the audience are actually electrical and computer engineers. It's helpful to understand what's actually happening in surgery. So there are three keys to a successful surgery. So the first thing is the detection. Essentially, you want to understand where is the disease, where is the lesion, and what is diagnosis. And for that, optical imaging is a wonderful platform that can offer many capabilities. The second thing that is important is the decision support. So as the surgeon conducts the surgery, he may have to know that, is the pedicle screw being placed at the right place? Is the drill pass being aligned? Or how can he or she correlate the two different modalities of imagery together? So for that, computer vision can play a key role. And last but not least, actually the more importantly, is the surgical visualization. Because surgeons really rely on the vision to make a determination where to cut and where to preserve. So visualization is very important. Currently in the operating room, surgeons use two ways of visualization to enhance their visualization. The first way is to use something called surgical loops, as shown on the left. So those are simple magnifiers. So they use those magnifiers to see a magnified view of the surgical field. On the right is showing those are monitors. So in addition to using the magnifier, surgeons also use the different monitors to see digital information. And you could imagine it's actually rather hard to do because you have to look at the patient, look at a magnified view, and also look at different monitors. So that is where augmented reality can come in to really enhance surgeons' capability. So speaking of augmented reality and virtual reality, here is a high-level overview, right? So usually when we visualize things with our own eyes, those are real visual information. Alternatively, we could also have computer generate those information and display to us, right? So that is called the virtual reality. And somewhere in between, you could have digital information overlaid with real environment. That is called augmented reality. In terms of the implementation, there are a couple of ways to do that. There are actually 4 ways to do that, right? So the first way is called a non-see-through configuration. So where all visual information are computer generated and you don't have any real world imagery. So a non-see-through configuration for something you might be familiar with the Facebook Oculus. So that will be a headset that's non-see-through and just VR only. The second way to do to instrument and implement a AR headset is so-called compact offset. So essentially, you can look around the digital display, right? As shown here, but you can look around it. So that way, you could either look at the virtual information or look at the real world. The third way is called the video see-through configuration, where you can use cameras as your eyes, right? So you can gather information through cameras and display that through the micro display to your eyes. So everything you see is digital, but part of the digital information is captured by the imagers and sensors in real time. And the last approach is called optical see-through approach, where you have a half transparent mirror called a combiner that combine the digital information being projected to you as well as the real world. So a Microsoft HoloLens will be an example of optical see-through AR headset. So speaking of AR and VR, it's actually not a new concept. Let me briefly walk you back to through the history. So actually, you can see this is the 1895 version of phonokinetoscope. So this person essentially is trying to watch a movie by looking into the eyepieces. This version, the phonokinetoscope actually predates. This came before the emergence of big screen movies. So it's very interesting. Actually, VR AR was the first modality for movie watching before you have big screens. In the surgical arena, during World War I, surgeons also used a early version of fluoroscope to detect where the bullet is, right? So you can see the X-ray sources down here, and the detectors up here, right? So this is the early version of virtual reality. And with the emergence of computer, the ability of the operator is being enhanced. So on the left is so-called Sensorama. So this is dated 1962. So they have a pair of color display, CRT display, fans, older emitters, and the surround sound system, and also a motion chair. So this system can simulate a motorcycle ride. On the right is the famous Sword of Damocles by Ivan Saraden. So this is so-called the ultimate display. At the time, due to the weight constraint, the system has to be mounted onto the ceilings and supported by the mechanical structures. But you also have stereoscopic display. So if we come back to this day and age and look at how AR and VR being implemented, this is the high-level overview. Right? So on the left, you have the inputs. The inputs can be different, put into different categories. It could be optical detectors, like your regular color camera. It could also be a fluorescent camera, thermal camera, or even a detector of Cherenkov radiation. You could also have imaging systems, such as ultrasound, fluoroscope, which is dynamic X-ray, CT, or MRI. And on top of that, I could have sensors such as gyroscope, which is including your IMUs, body sensors, eye trackers, and tracking systems. Right. So in addition to that, you could also have speech, voice recognition, and some traditional I/O input like mouse, keyboard, touchscreen, right, or gesture control. So with those inputs, the data can be processed on a computing platform, whether it's an embedded system, whether it's on the cloud, whether it's on the edge, and you can generate the virtual world, which can be rendered in 3 different ways. The most common way is a visual renderer, where it gives you videos, images, or text. Right? So in the medical domain, we use this a lot. Our renderer can give you the sound and speech, which can also be helpful. Haptic renderer can be also useful in the sense that they can give you feedback for force, vibration, and motion. So this could be very helpful for simulations, robotics, and other type of AR and VR applications. So far we have talked about how to build a AR system on a high level, right? But individualized AR systems have limited impact. So with the help of the network and with the help of computer vision, we can really expand the impact of it. So imagine you have sensors, cameras, and imaging system. You could construct a network, right? Whether it's WPAN or WLAN or WMAN, to connect them together. And with more than 1 image sensors and multiple cameras, now you can use those data and use computer vision to do a lot of very interesting tasks, such as image registration, which is alignment of 2 different imageries, image recognition. You can use neural network for deep learning. And because we're focusing on medical related applications, cybersecurity is extremely important, and you need to be HIPAA compliant for patient safety. Right? So with the addition of network and addition of computer vision, we can enable so many different applications, such as smart healthcare, smart transportation, industry 4.0, and military transformation. For today, we're going to focus on surgical applications. So far we have talked about what AR can do and how can we deploy that with a network. Here now is time to have a quick overview of medical imaging modalities. So here I am showing you 6 representative modalities. The 3 modalities on the top are the so-called structural imaging modalities, including computer tomography based on X-ray, CT, magnetic resonance imaging, MRI, and ultrasound. So you can see that they're very good at visualizing mechanical structures, right? So for CT, you can image the attenuation of the different tissues. So for bony structures, you can see them rather well. For MRI, it's really sensitive to soft tissue and provide a good contrast. You can see that there's a lesion here, right, in the disc. And for ultrasound, using mechanical waves, you can detect the echo, and you could essentially form a very nice image without introducing any radiation. So here you can see actually a contour of a baby. So on the bottom, we have pulse emission tomography, PET, and single photon emission computed tomography SPECT. So those 2 are so-called nuclear medicine, where you use radionuclides to as a source, and your detector force an image. So on the left, those are actually tumors. On the right, this is a perfusion study for the heart, so the cardiac perfusion. So in addition to those traditional modalities, optical imaging modality have also been widely used in different applications. For optical imaging modalities, a lot of them provide functional imaging capabilities, but some of them also provide structural imaging capabilities. So far we have overviewed the different medical imaging modalities. Applying them to the operating room for surgery needs additional consideration. So as we know, there's a department called radiology, which is focused on diagnostic imaging. So they have certain requirements which inspire the development of a lot of instruments. However, not all of those requirements are the same for surgeon. So for example, one of the important things for surgeon is the resolution of field of view. And this is really have to be looking together in totality, because you can have very high resolution, but usually it means a small field of view. You could have a large field of view, usually means not so good resolution. If both are optimized, the speed is usually very slow. So a trade-off has been considered here. For intraoperative imaging applications, the speed and latency is important. And real-time imaging is really preferred rather than waiting for 30, 40 minutes. Right. In addition, the surgical guidance is very different from diagnostic imaging because the users are different and they want different things. And for surgeon community, you also have different subspecialties. So plastic surgeon may have different things they want from a cardiac surgeon or orthopedic surgeon. So you have to essentially take those into consideration. And finally, the safety and radiation is an important factor. So fluoroscope, which is based on X-ray, and also the CT, which is based on X-ray, are very good, but they use ionizing radiation. Similarly, SPECT and PET also use ionizing radiation. That poses a lot of safety concern for the patient as well as the surgical staff. Right. But last but not least, the cost of workflow. How broadly can you disseminate the technology, and how can you integrate that with the hospital workflow has also need to be considered. And because of the very extensive list of requirements, optical imaging really stands out because it can offer high resolution with big enough field of view for the surgical field. It can be real time and provide both structural imaging and functional imaging. Very safe to use because optical imaging doesn't use ionizing radiation and can be low cost. So that's why optical imaging is really becoming a promising solution for intraoperative image guidance. Speaking of optical imaging, on the physics side, we're focusing on this bandwidth from ultraviolet to infrared. Just to refresh your memory, for PET and SPECT, you actually use the gamma ray. For CT and radiography, you use X-ray. For optical imaging, we focus on this spectrum. In terms of different technologies and modalities of optical imaging, here is a short list. It's not exhaustive. So you have fluorescent imaging, OCT, DOT, confocal and super resolution microscopy, photoacoustic imaging, and Cherenkov imaging. The latter two are hybrid modalities. So photoacoustic imaging is halfway ultrasound. Cherenkov imaging is optical detection of radiation. So for today's talk, we're gonna focus on fluorescent imaging, which is widely used for clinical functional assessment. Here's a quick background about fluorescence. So fluorescence is a phenomenon where a molecule, so-called fluorophore, can absorb a photon, goes into the excited state, and come back to the ground state through radiative transition, and in this process emit another photon. The interesting thing about fluorescence is that your excitation and emission have different energy levels. And that allowed a very easy way for spectrum separation. Essentially, you can separate your signal from your background. So that's very desirable. And conventionally, fluorescent imaging has been used extensively in the research arena, both in vitro and in small animals. So on the top are images of in vitro fluorescence microscopy. You could image processes at different levels, right? At the tissue level, cellular level, or even subcellular level. You can stain different structures with different fluorescent labeled antibodies or peptides. For small animal imaging, this is also very widely used. So with the emergence of different fluorescent labeled antibodies, peptides, nanoparticles, you could use those probes to image different processes. And more recently, fluorescent imaging has also been applied to a clinical setting. So here is a video of a representative clinical fluorescent imaging system, the Novadex Striker SPY system. And this can be used for image tissue perfusion. So you can see that this is the fluorescent imager. The surgeon can place this in front of the, actually on top of the patient, right? So here you see the fluorescent image. So you see in the middle, this is very dark, and the surrounding is very bright, which indicates potentially this is an area of necrosis, and the tissue is not very well perfused because the indocyanine ring, the 404, cannot get into those areas. And this is very helpful information for the surgeon because using that information, they can prevent tissue necrosis and prevent the chance of resurgery. And usually, the surgeon uses a monitor, and you can see that system is very big. It actually needs a specialized team to transport the system into the operating room and set it up. The setup can take actually from 15 minutes to 45 minutes. If we survey the clinical fluorescent imaging system on the market, here are some candidates. What we saw in that video is the so-called Novadex SPY Lite. That's this one. And you can see the other ones look more or less similar to the SPY Lite. Some of them are handheld systems, but most of them are actually car-mounted system. Those systems are great to offer a clinical decision support for the surgeon. However, the drawback is that when the surgeon is using the system, they have to use their hand to either hold the system or to move the imager, and they have to look at the screen. Sometimes the monitor screen is in front of them, across the patient, at the other side of the surgical bed. Sometimes those monitors are actually behind them, so they have to look behind their neck. So it's really not a good workflow. Just to recap the challenges, right, in the operating room of using fluorescent imaging and other imaging systems, you display the images on the monitors, which means the surgeon have to look away from the surgical site, and you have poor hand-eye coordination because you're looking at one thing and you're operating on the other thing. And the monitors are 2D, so there's no depth perception. And the surgery is 3D, and depth perception is very important. So this can potentially compromise the surgical accuracy. And last but not least, we talk about the complicated workflow by having the big system transported into the operating room and transported out. That can take between 15 to 45 minutes. In the United States, every minute in the operating room costs about $150 on average. So 30 minutes is $4,500 being wasted. To overcome those challenges, in the past decade, our lab have been looking at different solutions to solve this. One of the technology we come up with is called the smart goggle. It's a real-time imaging and augmented reality platform. So on the left is a prototype of our smart goggle, which is featured by CMDC. It offers variable stereoscopic fluorescent imaging and 3D display. Right? So on the right is a represented image of human liver cancer. So you can see the tumor is being pseudo-colored in gray. So in this particular case, the fluorescence is actually in near infrared spectrum, which cannot be seen by the human eyes. But the system can detect it and pseudo-colored as green. And right now we have a few IRB approved clinical trials going on in Cleveland Clinic, so we're very excited about it. So in the past 5 years, we have developed several different generations, several different implementations of the smart goggles. So here I'm showing you one of the prototype. So for this particular one, we're using LCD micro displays, and we have 82% binocular overlap. And the fluorescent imaging can be operated at a frame rate at 30 frames per second. So the person, operator doesn't visualize the latency. The system is lightweight, and the operator can wear them comfortably. In terms of resolution, a typical system we develop can detect down to 0.1 millimeters, so which is very good. And we have also characterized the fluorescent detection limit of those systems. So here you can see that the concentration of different fluorophores are plotted towards the pixel rating, right, at different working distances and at different molecular concentration. So you can see that we have very good linearity, and our system can detect down to 2 nanomolar of inositide grain. That's very impressive. So in addition to ICG, inositide grain, we could also apply the system to other tracers such as quantum dots or Alexa 404, or as well as Phi-ALA. So far we have developed a system. We want to apply that to a realistic setting similar to surgery. And one of the challenge in the operating room is that the surgical room light will bleed through, which add background to fluorescent detection. To overcome this problem, we use interleaf acquisition, where we essentially paused our fluorescent excitation. We assign an even frame for fluorescence and an off frame for reflectance. So this video illustrate the process, right? So essentially, by using interleaf acquisition, we could separate fluorescence from reflectance. So on the right is the process data, where you could visualize fluorescence much better. So far, we have overcome the problem of the surgical light bleed through. So in the operating room, one of the other problems is that if you are a variable system, there will be motion artifacts because the patient will be moving and the operator is moving, right? So if we're imagining when you subtracting the sequential frames from the previous slide, if you have a still target, right, you can nicely identify the fluorescence. But when we have a moving target, we have motion artifacts, right? So in this particular case, in addition to fluorescence, we also detect a lot of motion artifacts. So how do we deal with that? So that's where computer vision come in. So in this particular example, we actually combine dense optical flow with the interleaf acquisition to track the pixels. And this way we can identify the fluorescent pixels. So on the left is the video without optical flow tracking. on the right is with pixel tracking and fluorescent pixel identification. You can see that we can remove all the motion artifacts. So this is a nice example of hardware-supported computer vision. So far we have established how can we overcome motion artifacts. So in a surgical situation, in addition to the function of fluorescence, the surgeon is also interested in visualizing the surgical field, the structure information, which can be provided through color imaging. So how do we combine color imaging and fluorescent imaging? One of the new way to do that is actually through feature-based image registration. The challenge the community have been faced in the past is that you don't have similar features in fluorescence and color imagery. So however, with the previous method we already deployed, we can separate the reflectance component from the fluorescent component and use the reflectance component as a bridge to register between the color image and fluorescence component. So in this particular example, we extract the feature map from the reflectance component and the color imagery using deep learning and register together. So this way, the surgeon will have fluorescence information overlaid on top of the color imagery. So using deep learning is great, and using a computational method is great. However, that might at a edge deployment situation, that could be computationally heavy, and that might introduce a little bit of delay. So in an alternative approach, we have developed a framework for fluorescent to color image registration using distance-aware approach. So on the top is a version of our prototype. You can see that we have two color cameras and we have one fluorescent camera, right? So what we did is that we can extract the depth information and allow one-to-one mapping from the fluorescent image to the color image using the depth information. And this algorithm has been implemented in real time, and it has been very robust. So here are some representative data of characterization. So you can see that this is the testing platform we built with different tap depths. And then we have put different tubes containing solutions in them. Some of them contains indocyanine grain, which is fluorescent, and some of them contain just saline or water, which is not fluorescent. You can see that if you just apply a rigid transformation, it's really only good at one distance that you're calibrated for. At any other distance, you're going to have an offset. But with a distance-aware co-registration algorithm that we have developed, at any working distance is perfect register. So far we have talked about how to implement fluorescent imaging and augmented reality for wide field of view imaging, which is really good for assessment of tissue perfusion, look at the general surgical site for assessment. Sometimes the surgeon are also want to look into a particular part of the lesion to make sure, okay, do we have a clean margin? Do we take out all the lesion we want? For that, you actually need multi-scale imaging and augmented reality. Towards that end, we have developed a intravital fiber microscope I've shown here, and we coupled that with our smart goggles system, as shown this in the figure on the right. So we display the wide field of view image and the intravital microscopy imaging in a picture-in-picture format. So the surgeon can use the wide field of view to survey the surgical field and take a deeper look and closer look of the specific place of interest with much higher resolution. Part of our ongoing work is to implement active microscopy vision, where we plan to do AR-guided automatic placement of fiber microscope using an actuator and a robotic platform. And then in long term, it'd be great that we can enable human-robot surgical teaming. So far we have talked about how we can use our system in a preclinical setting and how we can characterize them. Now it's time for in-human imaging and clinical translation. So with our collaborators at Cleveland Clinic and other hospitals, we're able to apply our technology to a variety of applications. So here's one application. It's called sentinel lymph node mapping. This is the gold standard for cancer staging for many cancer types, including breast cancer and melanoma. So in this particular case, the fluorescent tracer is injected here, and you can see that they drain to the different nodes. And under fluorescent guidance and other image guidance, you can take out the sentinel lymph node. So ex vivo, we have confirmed that the sentinel lymph node has a higher concentration of fluorescence. And here's the videos of sentinel lymph node biopsy under fluorescent guidance. You can see that the near infrared fluorescence is still colored in green. To summarize, for the Smart Goggle project, we want to recreate a familiar user experience and minimize learning curve. So instead of using a simple magnifiers, the so-called surgical loop, we want to equip the surgeon with the capability to visualize functional imaging information in real time. So in the next few slides, I'm going to shift the stick a little bit, and we're going to look at a slightly different problem in surgical navigation. So in the surgical arena, one of the problems surgeons facing is the image correlation and surgical uncertainty. So in a typical case, surgeon is presented with preoperative image information, such as MRI. So in this particular case, you can see that the patient is rather unfortunate. He or she has a essentially a high-grade glioma here, as reviewed by MRI. During the surgery, the lesion is exposed, and surgeons start putting markers to mark critical structures. And occasionally, some surgeons also bring the fluorescent imaging system if they are available. So for high-grade glioma is cleared by FDA for fluorescence cleared by the FDA for imaging. So here you can see that fluorescence outlines the potential cancerous lesion. One of the difficulties to correlate, the surgeon have to face that, how do you correlate the different imageries with surgical site? This can be rather difficult. So that's part of the reason why in a lot of cases you have suboptimal surgical outcome. So you can see in this particular case, the cancer actually was not completely removed. When we dig into the evidence-based psychology research, we found that this is actually a well-documented phenomenon in psychology. So when you have multiple streams of information, your attentional resources being spread out very thin, and your response time is slower, and your response is more error-prone. Right? So, for example, if you have to look at preoperative imagery, intraoperative fluorescent imaging, and look at the surgical site, that's a very complicated process, which introduces dual task interference. It's essentially similar to asking, similar process will be test and drive at the same time, right? So we all know that we cannot test and drive at the same time because it's not safe. But in a surgical arena, surgeons are asked to do something that's actually more challenging than that, because they have to look at different images, different data, and also look at the surgical site and do the surgery. So if there's a way to consolidate this and combine all the information in one string, there's going to be lower demand of the attentional resources, and the response time will be faster, and the response will be less error prone. So to solve that problem, we have come up with to develop a system, we call it FITS, which can offer multimodal imaging and surgical navigation. So here you can see we combine color images, fluorescent images, as well as surgical navigation together. So in this particular case, if you look at figure E, right? So you can see color reflectance, and you also see fluorescence, which is reviewed by the green color. Actually, you could even see the lymphatic vessels in the rodent, which is less than 1 millimeter. Right? And on top of that, you could also visualize the CT data. Right? So in figure G, you could also see the scanning data. So instead of have several monitors here and there, the surgeon can have all the information in front of their eyes in 3 dimensions. So this is very exciting. So having accomplished that, we then move on to tackle another clinical challenge. So the challenge is the fiducial-based surgical navigation system. So for those of you who are not familiar with surgical navigation, you can think of surgical navigation as a GPS system using in the OR. So in the GPS, you're tracking where a car is using a satellite, and you are tracking where you are based on a map that's pre-generated. So in surgical navigation, it's a similar process. You use preoperative CT or CT data or a intraoperative CT data as your map, and you track where you are using markers, and those are called fiducial markers. Part of the problem is that patient moves, and those markers, like such as the reference frame, actually can be kicked or can be bumped, so your accuracy would decrease. In those cases, you have to redo a image registration, which calls for a intraoperative CT or intraoperative MRI scan and reconstruction, which can take up to 30 minutes. And this is very slow, and it's not very realistic. And with each of the intraoperative CT scan, you're also exposing the patient and the surgical team to additional radiation. So to overcome that, we have come up with a new system that can allow real-time surgical navigation and also fluorescent imaging. So here's a video. You can see that the CT data is represented in yellow, and the near-infrared fluorescence is represented in green. And as we're moving the target, the image registration and surgical navigation is being updated in real time, so with very minimal delay. So instead of waiting for 30 minutes for image registration and imposing additional radiation, surgical navigation can be updated with accuracy in real time. So here's another video you see. So here's the testing phantom. You could see the surgical navigation is being updated in real time. And one of the beauty of the system that we don't need any fiducial free, or we don't need any fiducial. So the whole system is fiducial free. We're using computer vision for image registration instead of using markers and fiducial. So having demonstrated the application of the system in cranial applications, we have also applied that to other applications such as spinal applications. So here on the bottom, you can see that the system have been used in cadavers. So we have spinal nerves that are fluorescent labeled. Right. We also have vertebral bodies. So here the vertebral bodies are being registered to CT data, and also we could image the spinal nerves that is fluorescent labeled. And this is very promising because essentially the system allowed the surgeon to make a clinical decision in a much easier way, where they can visualize where the hard tissue is, where the bony structure is, as well as where the nerves are. With real-time image registration and surgical navigation, the surgeon can essentially save time and have a higher accuracy. The next goal we had is to seamlessly integrate surgical planning with surgical navigation. So this video shows that how we can monitor the position of a tool and make sure it aligns with the planned drill pass. And this way, all the surgical planning data can be ported over into the surgical navigation platform. And the operator will have the feedback in real time. So in the past 3-4 slides, we have talked about how the system we develop can help a cranial application as well as orthopedic applications. In addition to those, you could also use them for perfusion assessment. So in this case, you can see that indocyanine green is being injected. And very soon, you could monitor the status of an area to see whether the area is well perfused or not. As shown by the system, this area has a peak fluorescence around 30 seconds. And after that, the fluorescence value would actually drop. And because the system is quantitative, essentially we can make a plot of the fluorescence perfusion, which can shine additional light into the status of the status of perfusion of the this particular area of tissues. So for plastic surgery, this is very helpful because you can use the perfusion study to determine the viability of the flap. A flap is a tissue that's transplanted from the donor side into a receiver side, and the perfusion and tissue viability is very important to indicate whether those flaps will survive or not. So in addition to fluorescent imaging, surgical navigation using CT MRI, we have also looking into integrating the ultrasound. In many applications, ultrasound can be very useful. So we have tried to approach using LEDs or using glyphs to register fluorescence and ultrasound image modalities. So here's a video to show you that how that works in real time. Furthermore, we have also looking into building systems and using a system to guide vein visualization. So in this study, we have imaged 25 human subjects, and we have determined that the vein visibility is improved by more than 2-fold. You can see that on the color image, it's very hard to visualize the vein. But with multimodal image guidance, location of the vasculature is really highlighted. So with these different areas of research that we have embarked on, we hope we can solve the clinical workflow problem in a holistic manner. Instead of having surgical navigation, surgical microscope, fluorescent imaging, and traditional loop, we could have one platform that can present the information to the surgeon in real time in 3D in a very intuitive manner. So far we have surveyed different examples from our own the research of our own research group. In the next 2 or 3 slides, I want to briefly touch on some of very promising and interesting study that others have embarked on. So this one is surgical planning using HoloLens for face transplant surgeries. So Dr. Frank Papea and Dr. Brian Gatzman are collaborators of ours. So they have used essentially HoloLens to visualize the preoperative surgical plan. And you can see that the surgical outcome is very amazing. So for this particular patient, and this is a near total face transplant. It's very remarkable. And some other researchers and companies have also looked at using HoloLens for the image for surgical navigation and real-time image guidance. The advantage of using HoloLens is taking advantage of an existing platform that has a lot of resource to it. I personally think part of the limitation is that if you use the optical see-through approach, there might be some focal rivalries because your eyes are looking at one distance of the patient, but the virtual images might be at a slightly different distance. So here's another paper where they have developed a system to use a combiner, a half transparent mirror. So here you can see you have a projector to project digital information reflected by the combiner and to be visualized through the 3D shutter glasses by the surgeon. So it's a very promising approach, and it's very innovative. One of the area of consideration is that now you have this combiner directly placed on top of the surgical site. How to keep this part of the apparatus sterile will be one of the consideration to be figured out in the future. And last but not least, Cleveland Clinic and Case Western Reserve University have been using HoloLens for medical education, specifically the anatomy lab. Instead of using human cadavers, they could visualize the anatomy very nicely using HoloLens. And this is very promising and very applicable for remote learning. So with the ongoing COVID pandemic and more remote learning going on, this is really a great way to enhance medical education and medical training. So in this talk, we have discussed different areas where optical imaging, augmented reality, and computer vision can be applied to solve surgical problems. In the future, I personally think those are a few areas that might be interesting to look at. The first area is optical imaging and AR display instrumentation. So we need better instrumentation for better imaging and better display. And the part of the ongoing effort by many researchers is also to use deep learning to enhance computer vision. And on the translational and clinical side, broad clinical AR deployment will really push the field forward. And because surgical setting is a very specialized environment where the surgical team may or may not have access to the internet, the edge computing capability is of utmost importance. A lot of processes has to be deployed on the edge, not on the cloud. So that could be something that's worth researching in the future. Okay. And again, because AR is usually a variable system, so miniaturization is very, very important. So with that, I'd like to end my talk today. Thank you so much for your attention. I would like to thank my research group and our collaborators, as well as our funding agencies. Thank you so much for your attention. and I'm happy to answer any question you may have.
It looks like there's a question in the question and answer tool.
Okay. Yeah, okay, so I'm just going to read it for the audience. Fusing multimodal sensor data give more perspective. Some systems exist with ultrasonic and laser-induced ultrasonic waves and fluorescence for detecting, locating, and measuring the size of tumors. Have you got some comments on those techniques and use of those modalities? I personally think what this question outlined to is a very promising approach. I think the size measuring is a very interesting aspect and can be of a lot of clinical values. So I think one of the challenge of use laser induced ultrasonic wave, which is essentially photoacoustic, as I understand it, is that the deployment of photoacoustic imaging system. So I'm not an expert in photoacoustics. I know that the femtosecond laser is very expensive and the instrumentation can be quite complex. I think that's a very promising approach that someone can, the field can really push forward. Regarding their clinical applicability, I'm not very familiar, but I don't think there are many clinical photoacoustic imaging systems being cleared by the US FDA yet.
Are there any other questions? Okay, great. Thank you, Dr. Liu, for your exciting talk. We really appreciate you being a distinguished lecturer for IMS, and we look forward to hearing more from you in the future.
Thank you so much, Madison. Thanks, everyone.